Hello students, welcome to this lecture. In this lecture we're going to talk about Konigsberg bridges problem. And Konigsberg bridges problem comes from the city of Konigsberg that is located in Russia, but now it's in Russia, Kaliningrad. And this problem is about the river and the bridges that connect two islands to the mainland of the city, which is located on both sides of the river. So picture looks something like this, and it has 4, 3, 5, 6, 7 bridges. Actually, it's not exactly true. It was heavily bombed during World War II, so few bridges were destroyed, but they tried to restore them after the war. So let's look at the problem itself. So the problem was to devise a walk through the city that would cross each of those bridges once and only once. So basically you start at any place in the city, you have to go around, you have to use the bridge, all of the bridges, but only once, and come back to the same place where you started. There are some conditions over here, like you cannot swim, you cannot take a boat, and so some things that are not really interesting. And it was in the 1700s. In the 1700s, people were puzzled by this problem, which apparently they couldn't resolve. They couldn't answer yes or no. Is it possible or not? They couldn't answer. And indeed, it's really hard problem. So I would strongly suggest to stop the video and try it on your own. Just make this small picture and try to solve the problem. Try to see if you can go around and come back to the same place by using each bridge. So you have to use all of the bridges, but you have to use them exactly once. And it was so hard that no one can resolve it until famous mathematician Leonard Euler in 1736, and his name pronounced differently depending on the person who pronounces it. Some people say Euler, some people say Euler. So you just choose your correct pronunciation. I think the correct way is Euler still, but English-speaking world usually pronounce it Euler. But he was born in Germany, lived all around Europe, one of the most famous mathematicians ever lived. So in 1736, he visited the city and got interested in resolving this problem. So what was his logic? His logic was, first of all, he didn't really like how it's pictured on a big picture, so he decided to go like this. He decided to have a north bank on top, north bank on the top, then the river goes around it like this and like that, and then the river goes around the island over here, and it splits up around some other island here. So here is another island. And the bridges go in place here, 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 and here. There is one bridge connecting these two islands, right? And our water flows here, and water flows here. And there are two more bridges to build in my picture, bridges like this. So first he thought that this would be good enough to have this picture, but then he understood that if you locate it in the north bank, and here you have south bank, so basically he understood that it doesn't really matter whether you start here or here. You can represent it just with one spot, the whole north bank. because from North Bank you can go to the island, and from North Bank you can go to the island. So it's enough to represent North Bank with just a big dot. In island itself, it doesn't matter where you're really on the island, you can represent the island with a big dot. Maybe over here. And South Bank is also one dot, and here you have another dot, and so then you connect with the bridges. So two bridges go from North Bank to this island, then two bridges go from the island to the South Bank. There is one bridge going like this, and one bridge goes like this, and one bridge goes like this. And that's the picture that earlier was working on. And actually he created a big part of mathematics by working on this problem, which now probably a third of mathematicians are working in this area of mathematics. And this area of mathematics is called graph theory. Graph theory. And in our department, we have a dedicated graph theorist. If you want to talk to her, she's amazing. So, graph theory. So graph theory pretty much deals with the pictures of this kind, where you have dots connected with some curves. So graph theory deals with the graph, and graph itself consists of vertices, and edges. So vertices would be these things. These are the vertices on this graph. These are the vertices, and these are the edges. Right, these are the edges. There are a couple more here and here. All right, so we understand that in order to solve this problem, we have to talk a little bit about graph theory before we come back and try to resolve this issue. Because again, if you try it on your own, you will see that it's not that easy to answer until earlier tried to resolve this problem. All right, so let's start. We need some definitions. In mathematics, a lot of times we use definitions to describe things. We will define a graph G to consist of two things. Right, and you already know what two things are, vertices. So let's try to put it in writing. A finite, so you can count them, what that finite means. Collection V of elements called vertices, and that's why V, right, from V, the first letter of word vertices. Sometimes people call it points of G. So that's the first thing. And the second thing that we're going to need is a collection of edges. So a finite, again, finite just means we can count them. Finite collection of edges called E, from the first letter, edges of G, where each edge E links a pair of vertices called endpoints, of E, obviously. Sometimes it links the vertex to itself, or links a vertex to itself. So this defines the graph. We have two things that we described in this definition. And now, how do we picture the graphs? That's the next idea to discuss. So let's do this out. How do we create a picture for the graph? Graphs are pictured. I forgot to say that I uploaded. I created a link on our Moodle page for the good video about Konigsberg bridges problem. So watch it. It's pretty interesting in just 4 minutes watch. So it's really interesting. So let's go back to the graphs. Graphs are pictured by the diagrams. And you put them in the plane, so basically on a piece of paper in a simple language, in the plane. And each point from V, so from vertices, is represented by a dot. Or sometimes a small circle, Now edges, and each edge is represented by a curve, which connects endpoints. Or sometimes it connects it to itself, but it's really rare. So let's look at the example. In this example, we have the following graph. So let's try to make a picture. And usually give the names to the vertices. So let's call it A, B, C, and D. And vertices, you usually give some names. So for example, we can name them, like you can just put numbers on them. Sometimes people say E1, E2, E3, E4, and E5. Suppose we give those names. So basically, to describe the G, we usually have to describe 4 vertices, right? 4 vertices, namely A, B, C, and D. So comma, comma, comma. And 5 edges. 5 edges, namely E sub 1, E sub 2, E sub 3, E sub 4, and E sub 5. But usually in mathematics, that's not the best way to write things. Usually in mathematics, when you list things, you usually use curly braces. So usually people do this. They say V equal curly brace A, B, C, and D. And and for E, we have a list of vertices. So E sub 1, E sub 2, E sub 3, E sub 4, E sub 5. That would be set E. Vertices and edges. And a lot of times people, to denote E1, for example, what E1 does, E1 links A and C, so people sometimes write AC instead of calling it A1, people call it AC. Then, for example, for E4, you will get BD. So we're pretty much done describing this example, but for this example, let's have a little bit of a discussion about this point over here where on our picture E2 and E3 cross. So intersection of E2 and E3. That's really important for understanding what's going on. I really don't have a dot here, so it's not really a vertex. So in real life, that means they don't really intersect, right? Because the only intersection possible is at the vertex, but they don't really intersect here. So the intersection of E2 and E3 is not a vertex. It's not a vertex. So what could it be? It could be like a road with a tunnel under the other road. So it could be something like this. So it could be a bridge going over some other road. So it could be like a road like this, and then the other road, which is something like that. It could be something of this kind. So it's not really a vertex. It's not really an intersection. So they don't really intersect. So I'll put intersection in quotes, right? So not really an intersection. All right, so unless you have a vertex, it's not really an intersection. So a couple more definitions that we need for this class. So the next definition that we're going to talk about is is about this graph. Just an example: A, B, C, and D. And suppose we have an extra edge over here. So let's number our edges: E1, E2, E3, E4, and E5. And also, this is a vertex, this is a vertex, this is a vertex, this is a vertex. And there is another loop goes like this around C. So the two edges E4 and E5, you see, they both start at the same place and end at the same place. So they're connecting A and D are called multiple edges. That's one definition that we can put for this graph. Another definition is about this loop that we have. So the edge, I didn't really name it, so let's call it E6. The edge E6 linking vertex, which one? C to itself. Linking vertex C to itself is called a loop. It's called a loop. That's the name for this. And the last definition for this picture would be graph, and this is really rare. We usually don't really talk about them much, but again, they exist, so we'll have to define it. So graph without loops and multiple edges is called a simple graph. Multiple edges are kind of fine. There's nothing wrong with them. But again, if you have a simple graph, it has no loops and no multiple edges. So next, so maybe it's a good place to stop for this first lecture and keep them short and concise. So I'll see you in the next one. And please watch this video about Konigsberg bridges problem that is published on our Moodle page. It's just 4 minutes. It's very interesting and it's very nice.